Okay, so in this video, I am going to describe about propositional linear temporal logic. As in the previous video, we studied about the modeling formalism and how that particular formalism can be used to model something that can be input to a model checker. The second part which a model checker requires is the requirement in the form of formula specification. So we will be using the propositional linear temporal logic formulas to be input to the NuSMV model checker. So here is the syntax of propositional linear temporal logic. It can consist of ordinary Boolean formulas or Boolean values like true and false. It can contain some atomic propositions which are made up of conjunctions or negations. So we write A is element of some atomic proposition which are built up of either conjunctive formulas or negated formulas. Then we have a conjunction of two formulas, and we have a negation of a formula, and here we use this x, which means the next of some formula psi, and then we have a special case like phi until psi. So how to interpret these things? We interpret these things on infinite traces. For example, if I want to express this part A, which is an element of some atomic proposition, so I can simply draw it in this form. So this is an example of an infinite trace which continues. So I want to show what is meant by A. So A is some element of an atomic proposition, so it means A holds in the very first place. So if I talk about this next thing, this one, so I can write if this is my representation of some infinite trace, then next A means that A holds in the next instance or next instance of time, which may be, for example, a state on our model. In case as we discussed, like a deterministic Kripke structure in the last video. Then if we talk about this phi until psi, so we can write like A until B. So if again I have some representation of this infinite trace, so it means as long as A is true, and B is not going to be true, and when B becomes true, A will no longer be true. So A is true until B is true. When B becomes true, A is not going to be true, and this is the interpretation of A until B, or this until formula which we mentioned at the end of this recursive definition of linear temporal logic. And then we have these derived operators for the linear temporal logic. So what are these? First one is the eventually operator, which is usually expressed as a diamond, or in some cases you can also write it as F, future. So if I write eventually B, it means that, or in future B, I can write I can mention its interpretation on an infinite trace like this. So it means this is going to be, the B is going to be true eventually in some state or at some instance of time. So we can also write it its definition in the form of the until operator. We can write that eventually B is actually equivalent to saying true until B. It means on these states it was true, the some Boolean condition true was holding, and when B became true, then that true statement was no more true. Likewise, another derived operator is this, the global operator, which we sometimes represent by a box. So I can write always, it is also read as always, and sometimes we also use the notation G for representing. G psi, box psi are basically the same. Similarly, future psi or future B are the same things as a diamond B or the diamond psi. So we can write this as always psi to be not eventually or not future not psi. So this also tells me that this box and this diamond are the duals of each other. So if I pass this thing inside this, then this will become a box, and the double negation will become the original formula psi, and we can have this left hand side back. So if I want to give its interpretation in the form of the infinite trace, I can write something like this, or I can represent it in this way. Now I want to say, for example, box A means globally A, and this is also equivalent to saying GA. It means A is true on all the instances or all the states of this trace. So this is how we represent the global operator or the box operator. Okay, so we are going to use NuSMV for writing both a specification and giving input to it as the formal model. So we should be familiar how actually NuSMV follows which syntax to express these LTL properties or linear temporal logic properties. So the conjunction is represented by an AND in NuSMV syntax, and OR is represented by this vertical bar, and the negation is represented by this exclamation sign, and the circle or the next operator is represented by an X. Until is represented by a U in NuSMV, and the diamond or the future operator is, or the eventually operator is modeled by or denoted by an F in NuSMV, and the box operator is modeled by a G in NuSMV. So the derived operator, the OR and implication have the same interpretation as they have in PLTL or first order logic. Sorry, in propositional logic or first order logic. So now we do a little exercise in expressing some English language sentences into PLTL. So if we say that today is a Wednesday, we can just use the variable Wednesday, and its value true means that today is a Wednesday. So so now we are trying to model the days of the week in terms of PLTL. So tomorrow is a Wednesday. Now remember that one instance or one state of this model is going to be one day, one week day. So tomorrow is a Wednesday mean, and that next Wednesday. So we can just simply write next Wednesday or X Wednesday, which means that tomorrow is a Wednesday. So this is the LTL's way of expressing tomorrow is a Wednesday by writing X Wednesday. Now if we have a sentence like this, Thursday always immediately follows a Wednesday. Now we have to take care of this always. It is indicating that there is going to be a global operator and immediately follow the Wednesday means that right in the next state that the date Thursday occurs after Wednesday. So we can write in this form. We also make use of this implication. So Wednesday is, if Wednesday is true, then the next day is Thursday, and this holds always, means there is not a possibility that when Thursday will occur before a Wednesday. So this is a global fact, and in terms of weeks of the day, this fact is globally true. So therefore we use the G operator. And the next one is Saturday always follows a Wednesday. So we have removed that strict condition of immediately. It means that we can make use of some other operator which is less strict than this next. So we can write this as G Wednesday implies that future there is a day which it is Saturday which occurs after Wednesday, not immediately in the next state or next instance of time, but after maybe a few states or few instances of time. So this one is interesting. Yesterday was Wednesday. So we want to model past by making use of these temporal or future operators. So that this is how we model it. So we say that Wednesday is immediately followed by a Thursday, which is written in this form of this implication. That is, if today is a Wednesday, then the very next day is a Thursday, and we write that this is always true by making use of a G before this parenthesis behind the implication, and we connect it with a sentence or a predicate which says Thursday, which means today is a Thursday. As we said that we model today is Wednesday by just writing Wednesday. So when I write today is a Thursday, I can model it by Thursday, and this part on the left of end is telling me that Wednesday is followed by a Thursday. Means what was just before Wednesday or what day was before Thursday. So it is Wednesday. So I modeled past by making use of the next and the global operator. Now, okay, so now we need to know about some LTL identities which will be useful in when we are doing the work on test case generation automatically by making use of this model checker. So if we double negate some formula, then we get the original formula back as shown by this result. And if I pass the negation onto this OR operator inside the parenthesis, this is logically equivalent to saying that not phi and not psi. So means the negation has been distributed to both the components of the formula, and OR has changed into an AND. Similarly, this implication is logically equivalent to saying not phi or psi. So I showed this by means of the truth table in the previous video. You can look up there if there is some confusion. Now we have some LTL identities. So we just talked about this one on the previous slide also. If I pass a negation operator on to this G, this is transformed to an F, and when the negation is passed inside this, there is already a negation there, and a double negation of some formula gives back the original formula. So this is just this identity which has been used here. So if the negation is passed on to an X, X does not change, and the negation is passed inside onto the formula. So this is the second identity. Next case is of the distribution case. So if we say that globally phi, psi and phi hold, then we can pass the global operator onto the components. This is equivalent to say G psi and G phi. So this one is interesting, which will be used in our test case process. So we can split up this. I showed you on the previous slide that we can model some formula G phi by means of an infinite trace. So it meant that like phi is going to be true on all the possible instances. So what does this mean? I can simply chop this part off, and what remains is next of global phi. The next of globally phi, then next of this phi is going to be again globally phi is going to be true. So this is useful in the case of when we are modeling use case requirements by means of LTL properties or LTL formulas. So you know that a use case has a precondition, so we can use this part as a precondition. If it holds, then this may be the next case or the success scenario of the use case, which is supposed to be true after this precondition holds. So then we have this little exercise that we want to prove that negation of the future operator is actually equivalent to a global operator. So if we pass the negation past this f, then the f is transformed to a g, and the double negation of this psi will become the original psi. So these two are considered the duals of each other. And then the next is the case of distribution. If we have the formula future psi or phi, so we can distribute the future operator onto the components of the formula future psi or future psi. So next one is again an interesting scenario. So future psi is logically equivalent to say psi or next psi. So the interpretation on the previous slide of future, we saw that if I write future psi, so it is like saying that psi is going to be true and at some time in future. So it means that either psi is true here, or I can say that if psi is true here, or it should be true next in the future. So that is what saying, like either it becomes true here or here, so that we can write as next future psi. So that is how we use. So it's not necessary that it is true here or here. If it's true at any one of these, then it is sufficient for this formula to be true. So these are going to be useful when we are doing work on task estimation. So from the previous video, you might recall that we modeled a 2-bit shift register which had these 4 states A, B, C, and D. And the configuration of bits was this: that the A state had both the bit false, B state has bits 1 and 0, C state has a bit configuration of 0 and 1, and sorry, the D state has a bit configuration of 1 and 1. So now we are going to write some LTL properties or linear temporal logic properties for this 2-bit shift register. The first property we write is this thing. Globally, it is the case that if bit 1 is true in some state, then in the very next state, bit 2 is going to be true. Now we want to see what happens to this property on this model. So if we notice, then bit 1 is true on this state and bit 1 is true on this state. What the property is saying is in the very next state, bit 2 is going to be true. So the next state of this state is 1 along this path, and if you follow this path, this is again the next state. Similarly, the next state of state D is 1 along this path if we follow this transition of 1, and it is also along this path if we follow the transition of 0, state C. Now we want to check if bit 1 is true on state B, and then the next state is state D along this path, and here you can see that bit 2 is true, bit 2 is 1. Similarly, if we follow this path, again here bit 2 is true. It means if we follow the outgoing parts from state B, either for state transition read for 1 or the transition for 0, in both the cases the bit 2 on the next state is true, both on state C and on state D. Similarly, if we follow the paths for state D which are outgoing from it, first transition which is for the symbol 1, that comes back to the same state D, and here you can see that bit 2 is true. Which means on the on this path also, if in the current state D bit 1 was 1, and if we take the transition and D becomes the next state of itself, then bit 2 is true. So on 3 parts we have checked, and now we check this last path. If we take the transition of 0 from state D, we reach state C, and again we see that bit 2 is true here. So we found no path on which if we found bit 1 true in the current state, then in the next state we found always that bit 2 was true. So this property is going to be true. And we will see this when we input the model of this 2-bit shift register and this property to the NuSMV model checker, and when we execute this, we will see how NuSMV also shows it to us that this property is true on the model. We change the property a little bit. Here we say that if in some state bit 1 is true, and then in the very next state bit 1 is again true. So we see that bit 1 is true on this state and on this state. Outgoing paths from this state are this and this. And if we see the value of bit 1 on this state, so here bit 1 is true. So it means along this path the property is not violated. But if we look on this state, here you see that bit 1 is false. It means we have found one path on which bit 1 is not true in the next state if bit 1 was true in the previous state. Similarly, if we check for this state, here bit 1 is true, and if we follow this path, then bit 1 is true. But if we follow this path from state D, then bit 1 is false here. So now we have found out two paths on which if in the current state bit 1 is true, in the next state bit 1 is not true. So therefore this property is false for this model. So when we run this specification on the model given to the NuSMV model checker, so it will show this to us that this property is false, and it will also give us a counterexample. So the counterexample may be this one, or it may be along this path. So it will depend upon which counterexample the NuSMV's algorithm on the back end finds out, and we will see when we do it practically using the NuSMV model checker. Thanks.